Hello everyone, I'm Norman Wahlberger. In this famous math problem, we are looking at how to set up the theory of fractions. And we gave a theoretical development of that last time. But now I want to address the very serious computational challenges that this theory generates. So we started out by saying that a fraction was an expression a over b, where a and b are natural numbers. And for us, that's going to be the numbers 1, 2, 3, so 0 not included. We have an important notion of equality between two fractions, that a over b equals c over d, precisely when ad equals bc. And then we had the definitions of addition and multiplication. These are the primary operations for arithmetic. A over b plus c over d is AD plus BC all over BD, while AB times CD is AC over BD. Now this is a very convenient realm because we can also introduce division very pleasantly. A over B divided by C over D is defined to be A over B times the inverse of C over D. And the inverse of C over D is just D over C. So we get that this division is just AD over BC. So that's very pleasant because usually division is a complicated process. So here in this world of fractions, it's relatively simple, which is a very attractive aspect. But nevertheless, there are some serious computational problems with this. So why is arithmetic with fractions rather challenging computationally? Well, there's a number of reasons. The first one is a direct consequence of our criterion for equality. To tell whether two fractions are actually equal, we have to do this AD equals BC criterion, and that is generally sort of awkward or painful, or at least involves some additional work. So for example, suppose you have this fraction, 48175,983 over 9787785. And we want to know, is that actually equal to the fraction 16058661 over 3261595? Well, the only way we can tell that really is to multiply this A times that D and multiply this B times that C and see if those two products are actually the same. Not very easy to see just offhand. In fact, here the answer happens to be no. These fractions are not equal. Which brings us to the second computational challenge. How do you tell which of two fractions is actually the bigger one if they're not equal? So I've told you these two fractions are not equal, but which one is the bigger one? Yeah, that's also, a naughty kind of thing. It's not immediate. You can't quickly decide. So that means that if you're doing a lot of arithmetic and you want to compare what you're doing with what your friend is doing, you're always having to resort to this cumbersome notion of equality, in principle at least, to check that your answers are actually coinciding. The third reason has to do with addition. Okay? In ordinary natural number addition, we're used to addition being relatively simple. 5 plus 7 is 12, plus 9 is 21. Plus 4 is 25. It's relatively simple. It's kind of linear. The sizes of the numbers don't get that big. Multiplication is worse. If 8 times 9 is 72, times 4 is something, and times 8 is something else. It gets bigger faster. It's kind of an exponential kind of increase. Unfortunately, with fractions, addition is like multiplication is with natural numbers, but it's even worse. Because when you compute AD plus BC all over BD, you have to do these three products. There's also a sum, okay? So for example, suppose you wanted to add these three fractions. Now, wait a minute, these don't look quite the same as our usual ones. And the answer is not the same either because it's not with the forward slash. So we're shifting to a vertical form for fractions, which is more usual. And it's advantageous when the numbers start getting big and you really want to be able to compare things. This is a little bit, arguably takes up more room. This is a little bit more efficient. Okay, so it turns out that this fraction plus this fraction plus this fraction is this rather big fraction, even though we're just doing two additions. Okay, so The complexity of the arithmetic is much worse because of the multiplicative content of addition. And that's something that I've encountered a lot in my own work on rational trigonometry and universal hyperbolic geometry. I like to work over the rational numbers and like to make computations. And invariably what happens is that as the constructions that you're doing pile up, so as you do more and more of them, the numbers involved, the coefficients of the lines or the elements of the points, they just get bigger and bigger and bigger in general, okay? That's the price you pay for working with rational numbers. Now, this computational complexity is not lost on primary school students and their teachers. And so a good amount of the training with fractions and arithmetic with fractions amounts to developing additional tools or insights or approaches that minimize the computational difficulties, that make it a little bit easier for young people to do arithmetic with fractions. So let's look at some of these techniques. The first one has to do with the introduction of the idea of a mixed fraction. Okay, so suppose that we have a bigger than b, and then we can try to simplify the fraction a over b by converting it to a mixed fraction. What does that involve? Well, it involves, crucially, Euclid's division lemma, which says that if a and b are natural numbers, and a is bigger than b, then we can find unique natural numbers q and r such that a is q times b plus r with r less than b. And actually, I probably should augment that a little bit. Let's say natural numbers plus, where I allow also the possibility that 0 might come up here, okay? So in particular, this remainder could in fact be 0. It's going to be less than b. So this is telling us that if we divide a by b, okay, then there's a quotient q and a remainder r, and this remainder is less than b. And this way, q and r are unique. Okay, this is a fundamental property of sort of division of natural numbers. So for example, 47 happens to be bigger than 11. So if you divide 47 by 11, you get 4 times 11, that's 44, plus a remainder of 3. So the q here is 4, the r is 3. So that allows us to introduce an alternate way of writing a fraction. Instead of 47 over 11, we write it as 4 and 3/11. So this is shorthand for 4 plus 3 over 11. Where is this coming from? Well, it's sort of like taking this equation here and sort of dividing everything by 11. So if we divide by 11, we're just going to get a 4 here. We get 47 over 11 on the left-hand side, and this over here will contribute a 3 over 11. So this is another way of thinking what 47 over 11 is. It's an integer, or natural number, and then an additional possible fraction, but that fraction is going to be less than 1. In other words, the numerator is going to be less than the denominator. That makes it kind of manageable. It's a little bit easier to see how big the fraction is. So this is a good thing because for primary school students, in fact for ordinary people, looking at a fraction like this, especially if the numbers are bigger, it's hard to assess how big this number is actually, okay? We are thinking it's some number between 4 and 5. When we write it like this, we have a clear idea of sort of where it is on the number line and what kind of an absolute magnitude it actually represents. Okay? That's obscured largely by this a over b way of writing a typical fraction. So this is an important technique that brings a little bit more understanding of the geometrical or arithmetical meaning of fractions. And it can also be useful for the arithmetic of those. So let's have a look at this sort of alternate arithmetic that we can establish once we have the idea of mixed fractions. So for example, 47 over 11 plus, say, 86 over 9. If we write each of these as a mixed fraction to begin with, well, 47 over 11, we've seen that's 4 and 3/11. This one here, how do we write it as a mixed fraction? We divide 86 by 9. So it goes 9 times, because 9 times 9 is 81. And then there's a remainder of 5. So as a mixed fraction, this is 9 and 5/9. Now, if we want to add these things, we can then add the natural number parts separately. So the 4 plus 9 is 13. And then we have these two smaller fractions to add, 3 over 11 plus 5 over 9. And that's pleasant because, well, these are just smaller numbers involved, and so the arithmetic is more manageable. If we want to add these two things, we have 3 times 9, which is 27, plus 11 times 5, which is 55, all over the product 99. Okay, and this here is 82, so we get 13 plus 82 over 99. Now, sometimes you have to do a little bit more. So instead of getting 82, if we had gotten, say, 102, then the numerator here would be bigger than the denominator. And so we would be obliged to peel off some of that numerator. So we would write the 102 as 99 plus 3. And the 99 over 99 would combine with the 13 to give us 14. So the whole thing would be bumped up to 14 and I guess 3 over 99. Let's compare this with actually doing the original fraction in the direct way. 47 times 9 plus 86 times 11, all over 9 times 11. You have to calculate these things. 47 times 9 is 423. 86 times 11 is 946. So altogether we get 1,369 over 99. And one could check that, yes, this is the fraction that corresponds to this mixed fraction. What about multiplication? Well, we can also do that with mixed fractions, although it's not quite as simple. So the mixed fractions is more geared towards addition rather than multiplication. But let's see what would happen. So 47 over 11 times 86 over 9. So 4 and 3/11 times 9 and 5/9. So you allow me not to put brackets here. So what this is sort of amounting to is 4 plus 3 over 11 times 9 plus 5 over 9. And then we can think about that in terms of the distributive law. So that's 4 times 9, which is 36. 4 times 5 over 9. So that's a separate kind of computation that students have to learn. So 5 over 9 plus 5 over 9, okay, is 10 over 9. So doubling a fraction really amounts to doubling the numerator. Right? If you added another 5 over 9, you get 15 over 9. It'd be like multiplying the numerator by 3. So to multiply this fraction by 4 is effectively multiplying the numerator by 4. So we get 20 over 9. And similarly, 9 times 3 over 11 will be 27 over 11. And then the product of these two fractions is the product of the numerators, 15, over the product of the denominators, 99. And now you see that you still have to do some work because now you have to add these things together. Okay, so you could do that. How does that compare with just doing it directly? 47 times 86 over 9 times 11. Well, that's arguably simpler because 47 times 86 is just a single multiplication. That's 4,042 over 99. So the mixed fractions technique is helpful in some situations. It certainly allows us to more easily position a given fraction in the context of natural numbers, like where is it in relation to the other natural numbers. So in particular, it makes comparing fractions a little bit easier. So this is an important additional technology that students learn in order to be able to reasonably smoothly do fraction arithmetic. Now let's talk about another important sort of alternative or additional amount of information that students learn in order to be able to make addition of fractions a little bit more agreeable. So let's consider this example, 73 over 24 plus 15 over 16. According to the official definition, that's 73 times 16 plus 15 times 24, all over the product 24 over 16. We do these multiplications. We get 1,168 plus 360, all over 384. and then we add these, we get 1,528 over 384, and that's an answer. Now, let's just observe some additional little lemmas, okay, that help us to do arithmetic with fractions. So if we have a fraction a over b and we add another fraction c over b, then we get a plus c over b. You can check that. And another one, if you have a times r over b times r, well, the common factor of r cancels, as we've seen already in our previous video, and you just get a over b. Now we can utilize these two things to have another look at this thing here. So 73 over 24. I'm going to multiply both top and bottom by 2. 73 times 2 over 24 times 2. According to this lemma here, that's still the same. So now we get 146 over 48. And with the other one, 15 over 16, I'm going to multiply both numerator and denominator by 3 to get 45 over 48. Okay, so we've used this one here. And now we can see that the sum of 73 over 24 plus 15 over 16 is the same as 146 over 48 plus 45 over 48. But now we can use this lemma here, which tells us that if the denominators are the same, then adding things is very simple. We just add the numerators. So we get 146 plus 45, that's 191. So we get 191 over 48. That looks different from this one. Are they actually the same? Well, you can check they're the same. How do you check that they're the same? You have to multiply 1528 by 48 and check that you're getting the same thing as 384 divided by 191. It's a bit of a nuisance, isn't it? Yes, indeed. So anyway, this illustrates this alternate approach, which rests on the idea of a least common multiple. The crucial thing here is that 48, we didn't get that just out of the hat. 48 is a multiple of 24, and it's also a multiple of 16. In fact, it's the least common multiple. So that previous computation relied on the fact that the least common multiple, represented by LCM, of 24 and 16 is 48. And in general, what does that mean? If a and b are natural numbers, then c is the least common multiple of a and b, precisely when c is, first of all, a multiple of a and b, and secondly, that there is no smaller multiple of a and b. So for example, the least common multiple of 5 and 15 is 15. The least common multiple of 12 and 15 is 60, because 60 is 5 times 12 and 4 times 15, and there's no smaller common multiple of 12 and 15. For example, 30 doesn't work, or 24 or 48, it doesn't work. Okay, and here's a little bit more sophisticated example that shows you how the prime factorization of two numbers, if you have that, allows you to extract the least common multiple pretty quickly. So here we have some number which as a product of primes is 2 to the 2, 3 to the 6, 5 to the 4. And here's another one, 2 to the 7, 3 cubed, and 7 to the 21. And the least common multiple of this one is 2 to the 7, so you choose the biggest power of 2. 3 to the 6, you choose the biggest power of 3. 5 to the 4, you choose the biggest power of 5. 7 to the 21, you choose the biggest power of 7. All right, that's the least common multiple of two numbers if you have it as a product of primes. All right, so now we can explain the way a lot of students are actually taught how to add fractions. We could call this the primary school fraction addition method. Okay, so suppose you want to add a over b and c over d. What steps do you take? Using this strategy, the first thing you do is to find the least common multiple of the denominators. So you look at the denominators, b and d, and you look for the least common multiple of them. So that's the tricky part. That's doable if these numbers are small, and gets considerably more challenging as the denominators get big. So this is a technique that really is oriented towards relatively small fractions, or at least fractions with smallish denominators. So suppose m is the least common multiple of b and d. then when you find the factors r and s, so that m is r times b and n is s times d. So we've established that m is a multiple of b and a multiple of d, and now we want to know, well, what exactly are those multiples? So m is r times b, let's say, and s times d. And then to compute a over b plus c over d, and let's switch to vertical notation because it just makes it a little bit cleaner to write down. Then we multiply the first fraction, top and bottom, by r, so ra over rb, and by the previous lemma, that doesn't change the fraction. And we multiply the second one, top and bottom, by s to get sc over sd. And then we use the fact that the denominators here are just m. So we get ra over m here, plus sc over m here. And then we use the other lemma that says that if the denominators are the same, then addition of fractions is very happy. You just add the numerators. So you get ra plus sc over m. So it's certainly true that for a lot of small-ish examples, this is a more efficient, shorter way of adding fractions. It's also true, however, that when the numbers get big, this is much more challenging because finding the least common multiple of two big numbers is quite challenging. Okay, but in any case, you see here that to give young people technology that allows them to actually work in this theoretically convenient framework of fractions that the pure mathematicians like is actually quite a lot of work. We have to teach them these various ways, these various maybe tricks almost, or alternate ways. They have to remember quite a few things, okay, just in order to be able to do fraction arithmetic. But actually, we haven't yet got to the most important thing that they learn or ought to learn, okay? And for that, we have to go back to Euclid again. I'll tell you about that in my next video. Hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.